Okay, in this problem we have a 20 kilogram slender rod and it is rotating with an angular velocity of 5 radians per second. It also has a moment of 60 Newton meters on it, and we are asked to figure out what its angular acceleration is and what the reaction forces at this pin, at this hinge are. So let's start by drawing a free body diagram. And if I do this right, here's my pin. Here's going to be my reaction forces, and I'm going to do it this way. I'm going to say that because this is rotating and it's sort of rotating on this circular path, I want to use a coordinate system of normal and tangential coordinates. I'm going to define to the left my positive normal direction and down my positive tangential direction. And I'm doing this sort of looking ahead at how this is rotating and everything like that. So I'm going to have some reaction force in my tangential direction. Let's just call this reaction force T. And I'm going to have some reaction force in my normal direction. Let's call this reaction force N. Now I'm also going to have a weight, and this weight is going to be going through the center of mass, and that's right in the middle of this 3 meter long rod. And this weight is going to be equal to mass, which is 20, times gravity, which is 9.81. And I also have a moment of 60 Newton meters. So now I've identified all my forces and my moments. I want to go to the other side of this and draw my accelerations. So here's my midpoint, my center of mass, and let's call this G. I know if I'm rotating in a circular path, rotation about a fixed axis, I'm going to have two components of acceleration. I'm going to have a normal component and a tangential component. And that's really why I chose an NT coordinate system rather than XY. But if I do this, I'm going to have a normal component of acceleration that points back towards the fixed axis. So right here, it's going to be 20 times my normal acceleration, and I'm rotating downward, sort of this clockwise direction, so my tangential acceleration is going to be straight down, and this is going to be my tangential component of acceleration. Now, I also need to account for my moment of inertia, and this right here is going to be my moment of inertia about my midpoint times my angular acceleration. Okay, so now I can sum my forces in all these different directions, and I can pretty much solve for all my variables. So if I start by, let's do the normal direction. This is positive. Sum of the forces in my normal direction is equal to a mass times an acceleration in a normal direction. I have this Rn is equal to my mass times my normal acceleration. Now I also know this normal acceleration right here is going to equal to my angular velocity squared times r, so I can substitute that in. I have an angular velocity 5 radians per second. I have a length of my fixed axis, which is r, and if I plug everything in, I can get a reaction force at my normal reaction force, which is going to be 750 newtons. Okay, So now I can look at my forces in my tangential direction. And I guess I'll do that same type of substitution right now. This tangential acceleration we know is equal to alpha times the distance to the alpha times the distance to the center of mass. So if I sum all my forces in my tangential direction, I have positive is down, so RT plus my weight, which is 20 times 9.81, is equal to my mass, which is 20 times alpha, which I don't know, times RG, which is the distance to my center of mass, and that's half of 3 meters. And so I can sort of move terms around and get my reaction, my tangential reaction is equal to 30 alpha minus 196.2. Okay, so now let's look at my third equation. The sum of my moments around my midpoint is equal to the moment of inertia of my center of mass, this is center of mass, not midpoint, times my angular acceleration. What is my moment of inertia? Well, I'm going to have to look this up in the back of the book, a table of moment of inertias, and I'll get that a moment of inertia of this long bar about this point on it, or about the midpoint on it, is equal to 1/12 m times the length squared, and that's about this this midpoint right here. So this is equal to 1/12 times 20 times this length squared, which is 3, and this is equal to 15 kilograms meters squared. So the sum of my moments about my center of mass only has to account for this moment right here and this reaction force that's tangential, because my weight goes through my center of mass and this normal reaction force goes through my center of mass. So if this is my positive orientation, I'm going to have 60 minus this RT times the perpendicular distance, which is 1.5. And this is going to be equal to the moment of inertia, which is 15, times alpha. And I don't know what alpha is. However, I do have two unknowns, my reaction force, my tangential reaction force, and alpha, and I have two equations. So I can solve this system of simultaneous equations and get an answer. So I'm going to plug this reaction force of T in right here, and when I do that, I get 60 minus 30 alpha minus 196.2 times 1.5 is equal to 15 alpha. And if I clean this up a little bit, I'll get 60 minus 45 alpha plus 294.3 is equal to 15 alpha, and 354.3 is equal to 60 alpha by bringing alpha to the other side. And I can solve for alpha, and I get alpha is equal to 5.9 radians per second squared. It's positive, so it's going in the same notation, it's rotating the same way that I've said is my positive rotation. And now I can plug this alpha back into this equation right here, and I can get my reaction force, my tangential reaction force, and I get my tangential reaction force is equal to minus 19.2 newtons. So what's this telling me? This is telling me that this assumption that it's in the positive direction, it's going down, is wrong. My reaction force is actually 19.2 newtons going up. It's the negative sign just means it's going the other way.